Continuous function. Oscar, what are the hallmarks of a continuous function?
Because a continuous function, the line goes through all the dots and continues.
That's right. In a continuous function, any point on my function is connected by the same line. Doesn't have to be a straight line. It could be wavy, curvy, jagged, but it's got to all be connected, right? What does a discrete graph look like? Yeah. There's nothing connected. It's just a bunch of points in space. Nothing's connected, right? So if I look at number 1, yes, this section is continuous and this section is continuous, but because I have this little break in my continuity here, this would be neither, right?
Yes.
Now number 2, I've got a bunch of dots. There is a seemingly missing dot, but that doesn't matter at all. This is a discrete function. None of the points are connected by a line. Even though there's that weird little space that's trying to trick you, don't fall for it. It's discrete. What'd you guys get for number 3? Discrete. What about number 4? Continuous. What about number 5? Continuous. What about number 6? Neither. Again, we've got those breaks in continuity. What about number 7? Discrete. And number 8? Continuous. That's right. Number 18. Looks a lot like our warm-up, kind of. So, negative 9x plus. This is what we talked about yesterday. I think this was in our notes, right?
Yeah.
If I square this, Precious, what does that give me? Or did you have a question? Okay. What do I get when I square root 4 times x? 4x squared. 4x squared. Is my x underneath the square root? No. It's 2 separate things. So that's like saying root 4 times x squared. So when I distribute my exponent, you can't even see it. When I distribute my exponent, the square root of 4 squared, like we said, they cancel out, just give me 4. But x squared is x squared. So don't forget that little exponent. That's going to change a lot. In fact, it's going to change. Oh, it's not going to change that much, actually. All right. If I want to get this in standard form, I can subtract the 7x squared from both sides, line it up with my like term. I'm going to write this in order. Negative 3x squared minus 9x plus y equals negative 4. Is that standard form? No, because I've got this 3x squared here. If that guy wasn't there, would it be linear? Yes, but because he's still there, this is non-linear. Okay, what'd you guys get for number 12? Linear or non-linear?
Linear. Wait, no, non-linear.
Non-linear because I have a variable in my denominator. Right? What about number 14? Definitely linear. Right? That's y equals mx plus b. That's as linear as it gets. What about number 16?
Linear.
Linear or non-linear, number 16?
Linear.
Good. Linear. Yeah, Precious. One more time. 16? Sure. Where is that? Oh. Good. Yeah. I actually did want to talk about 16. So 16, I got 2y plus x thirds equals negative 6. Now, I know it's nonlinear when my x is in the denominator, right? If it's in the numerator, well, I can just fraction bust this out. If I multiply this whole thing by 3, right, the whole equation, both sides, I get 6y plus 1x equals negative 18. That's a nice standard form equation, ax plus by equals c, right? I technically don't even need to do that. I could just rewrite this as 2y plus 1/3 x equals negative 6. It's still ax by equals c. A can be a fraction as long as it's a number, a rational number, right? But if I tried to do that same thing in number 12, let's say I wanted to fraction bust number 12, y minus 1 over x equals 11, I'd have to multiply the whole thing by what? By x. Well, that'll cancel this denominator, but now I've got xy minus 1 equals 11x. Well, now I have another issue. I can't have x and y being multiplied together, right? That wouldn't be standard form. I can't split those up without putting another variable in a denominator. So this would be non-linear, right? So that's the difference. Don't just look at a fraction with a variable and say non-linear. It depends on where it's at. If I can bust it out, that's fine. If I can't, non-linear. Does that make sense, Precious? No? Cool. Thank you for asking that. 22. I see a table. I'm going to draw some arrows. Boom, 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 boom. How would I get from negative 10 to negative 4? Plus 6. What about from negative 4 to 0? What about from 0 to 4? What about from 4 to 6? Okay. Right away, that looks pretty non-linear, but let's check the other side. How would I get from negative 5 to negative 2? How would I get from negative 2 to 0? How would I get from 0 to 2? How would I get from 2 to 3? Plus 1. So again, I look at this and go, oh, all my changes are different. This must be non-linear. Well, let's put all these changes over each other. Right? 6 over 3, 4 over 2, 4 over 2, 2 over 1. What do all of these equal? 2. That is a constant change in x over y. This is linear. Give me a thumbs up. You got linear for number 22. Good, 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 good. Right? Because if I wanted to, I could expand this table out to include all my missing numbers. Negative 5, 4, negative 3, negative 2, negative 1, 0, 1, 2, 3. Now I'm going to have a 4 and a 6 with a 0, negative 10, and negative 4. Right? So just because I'm not looking at the whole table doesn't mean it's non-linear. Right? If I spread out all my inputs or my x values, I would see I've got negative 8, negative 6, negative 2, and 2. Nice and linear. Right? So just because I'm only showing you part of the graph doesn't mean we can make a generalization. In the same way that just because I see an exponent, that doesn't necessarily mean it's nonlinear. I got to simplify it first to find out for sure. Finally, you said number 24, right? Okay. Tamika wants to improve her running endurance and thus tries to run for longer periods of time each day. Okay, that's right away. I know that's, anyway. The distance she runs given the day is provided in the table. So my days, plus 1, plus 1, plus 1, plus 1, plus 1. Down here, I've got plus 0.25, plus 0.5, plus 0.75, plus 0.5, plus 0.5, plus 0.5. Is that linear? No, it's definitely non-linear. Now, if I were going to graph it, the reason why it says to graph it is to show you that it's not linear. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Distance, if we go from 2 to 5, there's 3 and 4. There's 2, 5, 3, 5, 4, 5. Right, it's not hard to sketch a graph. 1, 2 is right there. 2, 2.25. 3, 2.75. 4, 3.5. 5, 4. 6, 4.5. 7, 5. Okay? So I know it's obviously going to look a little wonky because I don't have a grid here, but does that look like a perfectly straight line to you? No. Again, there's only a plus 2.5. Then we go plus 0.5, plus 0.75, and then plus 0.5 all the way up. So because that's not a constant change, this is non-linear. What type of function is this? What can I describe this function as? Discrete. How do I know it's discrete?
Because the lines are connected but not straight.
Because there are dots, but they are not connected. The dots are not connected, which makes it discrete. Right? Does that make sense? A little bit? Okay. Perfect. Obviously, don't pass that up because it's in your notebook. We've already got it checked off. if you didn't have it done when I came by and checked it off, just show it to me when it's done, and I'll put it in the grade book. Just like any other assignment, give it to me when you're done, and I'll put it in the grade book. You all right? Okay. Take the next available page in your notebook for today's notes. You got 2 things we're gluing in, and I need everyone to have a yellow and a pink highlighter. And this time they must be yellow and pink. Here's our heading.
Mr. Church, you know today's number 60?
Oh, it is. Nice. That's our area code.
Those are your
Not look like